It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on design of foundations, which will be delivered by Emeritus Professor Harry Poulos. Emeritus Professor Harry Poulos is an Emeritus Professor at the University of Sydney, and also a Senior Consultant with Tetra Tech Coffee in Sydney, Australia. He has been involved in a large number of high-rise projects in Australia and overseas, including the Burj Khalifa in Dubai. He was the Australian Civil Engineer of the Year in 2003, and is a distinguished member of the American Society of Civil Engineers. In 2014, he was inducted into the U.S. National Academy of Engineering, and in 2020, he received the Peter Nicole Russell Medal from Engineers Australia for Lifetime Achievement in Engineering.
Hello again, ladies and gentlemen, and thank you for tuning in to the second part of this series of lectures on foundation design. And I'm going to talk this evening about the design of deep foundations, something that I've been involved with for, I guess, over 50 years. And the issues that I'm going to discuss fairly briefly, again, and I emphasize that I can't go into great detail on any of these. So the whole idea is that I give you pointers as to what the key issues are in the various aspects of design. So I'll talk about pile types and their uses, the effects of installation, which are very important in terms of the performance of the piles, axial capacity, settlement, and lateral response. And then I'll talk a little bit about the effect of ground movements, because they can be very significant for some situations. And finally, because Professor Das did mention I had some involvement with the Burj Khalifa, I'll give you a brief overview of that particular project. Again, these are four suggested references that you might wish to look at from time to time. This one, the book I wrote with the late Professor Davis, is out of print, but it is perhaps available on the dark web somewhere. But there's some very good books, Fleming and others, Tomlinson and Vigiani and his colleagues in Italy, that have written books subsequently. And an unashamed commercial bit here, I did in fact write another book in 2017 on tall building foundation design, which incorporates a lot of detail on the issues that I'll discuss in this lecture. Now, just before we start, let's get a perspective on piles. Most of us that do designs draw little long rectangles to represent the piles, and perhaps it's not always apparent how big units of these piles are. So these are a couple of diagrams from a book called Underground by David Macaulay that just give you an idea. Here's, for example, in this case with build piles, this is the human scale and this is the pile scale. So you can see we're dealing with extremely large units, even though they may just appear as a long rectangle on our design sheets. In terms of the types of piles, we can classify them by materials, and generally we use either steel, concrete, or timber, or a combination. We can describe them in terms of their effects of the installation process, displacement, low displacement or non-displacement piles. And I guess fairly commonly, we describe them by means of installation: driven piles, board piles, screwed jacked continuous flight auger piles, and a combination sometimes of all of those. And these are some of the piles. Driven piles, very familiar. Board piles, larger diameter piles you can put with board piles. Continuous flight auger piles that are quite commonly used, certainly here in Australia. And I'll also mention the barrette, which is really generally a fairly large rectangular pile and increasingly being used for very tall buildings. And I'll mention something about that right at the end of this talk. Now, coming on to the effects of installation, I've got here a little diagram showing three types or three situations of installation. The first of these is a board pile. And what we have to understand is that when you do an excavation for a board pile, you are actually relieving the stress, at least temporarily, in the ground, so that you've got a stress reduction. And so there may be some softening and reduction of effective stress in the soil. And so the soil may at least temporarily be weaker. And so a board pile initially perhaps will cause some local weakening of the soil. If you drive a pile in clay now, and that's generally done, of course, with a pile driving hammer, and if it is in clay, then you get temporarily an increase in excess water pressure because you create a change in total stress, and therefore you develop excess pore pressures. These dissipate with time, and so you would expect that there will be a time effect with the behavior of piles driven in clay. And if you drive a pile in sand, what you're doing is you're forcing the sand sideways, so you tend to compact the sand, and so the sand will finish up being in a different state to that which it was before you started the pile driving. So in a brief sentence, then the installation process can have a major influence on pile performance simply because the installation of the pile changes the stress state in the ground. And of course, the effective stress state governs the strength of the soil. If we just look briefly at some of the issues that we have to face with displacement piles and driven piles in particular, we generally do a form of pile driving analysis to assess the drivability, to make sure that our equipment can drive the pile to its required elevation, and that the stresses that we generate within the pile during driving are able to be withstood by the pile material. There are also issues sometimes with respect to instability of the pile during driving. We get a dynamic instability or flutter, particularly with fairly long, slender piles. And so that's something that we have to guard against. And as I mentioned before, there are time effects. Generally, the pile capacity will tend to increase with time after driving for both clays and sands, although there are some situations where you can actually have a reduction in capacity. So you always have to be a little bit careful about the longer term capacity of piles, even though they may appear to be okay when you first drive them. In days past, there were a whole series of pile driving formulae which assisted us in trying to assess the drivability of piles. And I think in a book that Chellis wrote in 1960, there was something like 467 pile driving formulae. Unfortunately, many of them are not reliable. And one of the oldest ones that I think people were still using some years ago is the engineering use formula. And it can be way out in terms of the safety factor that it actually provides. And so when people do use formulae, one of the most common is the Hiley formula, and there are others which are also less unreliable than some of the earlier pile driving formulae. But in recent decades, the use of pile driving formulae has been superseded by the application of wave analysis, wave equation analysis of piles. And these actually try and model the process of the hammer blow producing a stress wave down the pile. It moves along the pile at the speed of sound so that the entire length of the pile is not stressed simultaneously, but you get this wave that goes down and is reflected upwards. And unfortunately, the old theory on which pile driving equations were based was the Newton impact theory, which assumed that the whole pile was stressed simultaneously. Now, these days, pile driving formulae and pile driving testing using, for example, the CAPWAP process developed in the United States are very common and quite reliable. In terms of our design calculations, these are the things that we have to consider with deep foundations primarily. There are others, but these are the key ones. Ultimate capacity axially, settlement and differential settlement, load capacity and deflection, and the possibility that due to some external process, there will be ground movements that will affect our foundation. And in all of these cases, we need to be aware that there are group effects that we need to take into account, that the fact that we generally use piles in groups rather than as single units means that they interact with each other, and that will influence their performance. So coming on to the ultimate capacity of piles, I think it's well known that it's and accepted that the ultimate capacity of a pile, and we'll talk about a single pile first, is the ultimate shaft resistance plus the ultimate base resistance, leaving aside the sort of deflections that we require to generate the full capacity. But this is the capacity that you can generate if deflections aren't a problem. And you have an ultimate shaft resistance, which you calculate by summing up the shaft friction, the unit shaft friction, over the circumference of the pile along the length of the pile. And as far as the ultimate bearing, end bearing capacity is concerned, PBU, FB is the ultimate base resistance, and AB is the area of the pile base. So it's a very simple basis. It's a very clear situation. And our challenge here is to estimate relevant values of the ultimate shaft friction and the ultimate base pressure of the particular pile we're dealing with in the particular soil profile that we're dealing with. Now, I mentioned yesterday the concept of category 1, 2, and 3 methods, and I'll be focusing here primarily on category 1 and category 2 methods. Category 1 are simple empirical methods, and among these are methods that correlate the skin friction to SPT, standard penetration test data, or CPT, cone penetration test data, or pressure meter data. And then we'll talk about category 2 methods, which are simplified but soundly based, and I'll mention 2 that are commonly used, the alpha method and the beta method. And I should also mention that for practical design, we generally, regardless of what these calculations may tell us, we usually put an upper limit on the skin friction and the end bearing, simply because there are many uncertainties. So this is one of the category 1 methods using SPT data, that the skin friction is a value A multiplied by 2.8 times the SPT value plus 10, and that is in kilopascals, with that A being smaller for non-displacement piles, board piles, than it is for displacement piles, generally reflecting the influence of the installation of the pile on the skin friction. So that's a very simple relationship, and as a first estimate, it actually is quite a good starting point, because in most site investigations, we tend to have values of SPT available to us. As far as end bearing capacity is concerned, again, this is from Decor in Brazil. We multiply the average SPT value in the vicinity of the base by a factor K, which depends on the soil conditions, higher values for sand and for clays, and whether we're dealing with displacement or non-displacement piles. And we also then put a limiting value on the base resistance. We can also use cone penetration data. There are three general methods for doing this. One is using the measured sleeve resistance in the cone penetration test, which was something that Schmertman and Nottingham did way back in 1975. More commonly, however, we tend to use the measured cone resistance, and this has been quite well developed, particularly in France and in other parts of Europe. And again, is a very useful approach, particularly when we're dealing with softer soils. And the third approach is to use the cone penetration data to obtain soil properties, the strength characteristics of the soil, and then put those into a more conventional analysis. Getting on then to these conventional analyses, the simplified but soundly based analyses. As far as the shaft capacity is concerned, we use Coulomb's law that the ultimate skin friction has an adhesion component plus a frictional component, where here Ca is the adhesion, K is a lateral stress coefficient, sigma V is a vertical stress, and delta here is an interface friction angle between the pile and the soil. So we're just using Coulomb's theory that goes back more than 250 years almost. Now, from that theory, if we now specifically look at undrained capacity of piles in clay, that frictional component, because the friction is generally low or zero under undrained conditions with clays, we can simplify the approach and say that the skin friction is a parameter alpha times the undrained shear strength. And this alpha, in fact, is a function itself of undrained shear strength. It goes from about 1 with very soft clays through to something like 0.25 to 0.3 for stiffer clays. So this there's a simple approximation that Kulhawi and his colleagues developed here that gives you, again, a first estimate of the skin friction of piles in clay when you've got undrained shear strength values available. The beta method, which is the other basic method, assumes that for long-term capacity of piles in clays, or for the capacity, the shaft capacity of piles in sands, that the skin friction doesn't have a cohesive component, no cohesion component, but it is basically dependent on the frictional component. And we generally simplify that frictional component to a value beta, which is multiplied by the vertical effective stress, where beta is the product of a lateral stress coefficient and the tangent of the interface friction angle. And there are certain approximations for sands and clays. And typically we find that beta is somewhere between about 0.2 to 0.3 for normally consolidated clays, and can go up to 0.5 or 0.6 when we're dealing with stiff clays and sands. So again, this is a very simplified but rapid method of estimating the skin friction in the longer term. Now, Stas and Kulhawi developed values of the K and delta in this previous equation that form the beta value. And those values, the interface friction angle values, depend on the nature of the interface and on the way in which the pile was actually installed. So these are the delta on phi dash values going from 1 down to about 0.5 if you've got steel piles with a fairly smooth interface. And also the effect of the installation method, they reflected in this value of Ks, the lateral stress coefficient, which was denoted as a function of the at-rest pressure K0. And if you've got drilled piles, bored piles, you have a value perhaps less than K0, so the Ks on K0 is less than 1, and for driven piles, it can be equal to or greater than 1. So these are just, again, some preliminary means of estimating the skin friction. If we come to the end bearing capacity, here now we're using bearing capacity theory. And if we've got clays and we're looking at the undrained capacity, which is generally the critical case, we can simply express the end bearing pressure as a bearing capacity factor NC multiplied by the undrained shear strength within the depth of influence of the base, typically 2 or so diameters below the base. And that NC value increases from 6 if you're very shallowly embedded to a value of 9 if your embedment is 3 diameters or more below the surface of the bearing layer. In sands, obviously, we don't talk about undrained conditions. We talk about long-term drain conditions. And so now we can estimate the end bearing capacity as a bearing capacity factor NQ multiplied by the vertical effective stress at the level of the pile base. And again, we usually put upper limits on that. And the NQ value from bearing capacity theory, this is from a Russian paper from 60 years ago now, shows the value of NQ increasing as the friction angle of the sand increases. Now, there are, of course, what I've been telling you so far assumes that you have all sand or clay. And that, of course, is not frequently the situation. Meyerhoff, in his Terzaghi lecture back in 1976, recognized this and indicated at least 3 situations that we often face in reality. The first of these is where we go from a weak soil into a dense sand, for example. And what Meyerhoff recognized was that even though you go from the weak soil into the dense soil, you need some amount of embedment before you develop a full end bearing capacity of the pile, typically maybe 4 to 6 diameters embedment before you get the full capacity. The next case, which is quite dangerous, is where you have a softer layer or a weaker layer below the sand layer or layer of soil in which the piles are founded. And what happens there is that the presence of that weak soil layer can reduce the bearing capacity as compared with if it was all dense material. And so if that weaker layer is closer than about 3 to 5 diameters from the pile tip, it can have a negative influence on the bearing capacity. And if we have a situation where you have a weak layer and then a stronger layer and then another weaker layer, you have to be, again, very careful because both the overlying and the underlying layers can influence that bearing capacity, and you may not be able to generate the full end bearing capacity that you would get in a dense sand simply because you have to go a certain distance into the dense sand. And if you then go too close to the weaker layer, then that again influences the end bearing capacity. So these are situations that you have to be very conscious of. And that's one of the reasons why we have to be very careful in characterizing the site and doing a proper site investigation to make sure that we identify any such weaker layers. Coming on to rock, we have generally correlated the ultimate skin friction and end bearing to the unconfined compressive strength of the rock itself. And this we've used quite a lot, particularly for weaker rocks. So you have a relationship, the ultimate skin friction is a value A times the unconfined compressive strength to some index B, and that's in megapascals, and a similar correlation for the end bearing capacity, but with different numbers for A and B. For skin friction values, many suggestions have been made, and I've got some of them here. I won't go into detail. But as a conservative first estimate, we often use 0.3 times the square root of the unconfined compressive strength in megapascals, and that gives you a skin friction in megapascals. If you have a roughened socket, then you can get substantially greater skin friction than indicated by this equation. And so one of the practical issues is that if we can specify that the rock socket is made rough, then we can get significantly better skin resistance than if the socket is smooth. In terms of end bearing, again, these are suggestions of those parameters A and B in that simple equation. This is Zhang and Einstein's approach, which we tend to use as a first estimate. It is quite conservative, but it's a first approach, gives you an order of magnitude. Now, one thing I'll just mention, and that is that so far we've been dealing with the capacity of piles in compression, but there are many issues or instances where we need to also estimate the uplift resistance of piles, particularly if we're dealing with lightly loaded structures or we've got big overturning moments. Now, if we're in clay soils, then the shaft friction is similar to the value in compression. So the uplift and compression values tend to be fairly similar. If you've got enlarged base piles, you need to also be aware that there may be two possible failure mechanisms. One is that the shaft and the base act individually together with the pile weight, but you can also have, particularly if you've got a fairly shallow pile with an enlarged base, you may actually get a whole pull out of the base. And so there you've got the gross base resistance plus the pile weight. And one of the things that you need to be aware of is because uplift does tend to reduce the stresses in the soil, it is possible that the long-term capacity of enlarged base piles in clay may be critical rather than the short-term capacity. In sandy soils, some very nice work that was done some years ago by DeNicola and Randolph clarified the effect of what's called the Poisson effect. Now, if you load a pile in compression, there is a tendency for the pile to sort of push outwards because you're compressing the top of the pile. And so you tend to get an increase in the lateral pressure between the pile and the soil. Conversely, if you're putting an uplift load on the pile, there is a tendency for the pile to contract horizontally, and so you get a reduction in stress between the pile and the soil because of this so-called Poisson effect. And so DeNicola and Randolph quantified this. I'm not going to go into detail on this equation. You can have a look at it. It's a nice paper in the ASCE, but simply to state that generally, if you're not really aware of some of these parameters, if you adopt in sands an uplift shaft friction, which is 20 to 30% lower than the value that you would use in compression, then that's probably going to be quite a good design assumption. Now, I've mentioned that the mechanism for the capacity of a single pile is fairly straightforward. I mean, you just got skin friction and end bearing. And you would think that we would be able to make quite good predictions of the capacity of the pile. So how well can we, in fact, predict the capacity of the pile? Well, Dr. Bengt Felenius, just a few years ago, worked on a test site in Bolivia where they tested 4 different piles and invited a whole bunch of predictors to predict the capacity and the load settlement behavior of the piles. And so they had quite a bit of data on the site. They had soil types, they had SPTs, cone stress data, and various other forms of data. So there's a lot of cone tests, and you can see sort of a reasonable pattern of a softer soil, a stiffer soil, and then a bit of a softer soil. How well can we predict? Well, the bad news is not very well. Here's one typical pile. This is a bored pile drilled with slurry. There's lode settlement. These blue lines are the predictions, the Class A so-called predictions before the fact, and here is what was actually measured. So you can see an alarming scatter of lode settlement predictions, and here's the lode distribution with depth showing again a capacity somewhere between 300 and about 3,000. So there's almost a factor of 10. So I find this quite disturbing, but I think it's also a salutary lesson that we have to expect that we may not be able to accurately predict the capacity of piles. So our prediction capability is quite poor, and unfortunately, that is consistent with what has happened with some past prediction symposia. And again, I'll just emphasize my hypothesis that in so many cases, it's not really whether we use method A or method B or method C, but on how we select the geotechnical parameters and how well we can convert the knowledge of the ground conditions we have into appropriate design parameters. Now, coming on to pile groups, very briefly, we have to recognize that when you've got a group of piles, there are two main mechanisms of behavior. The first is that each pile can act independently, and so the group will have a capacity which is equal to the sum of the individual capacities of all the piles in the group. So that's the first mechanism. The second possibility is, particularly if you've got piles that are fairly closely spaced, that the piles sort of hold on to the soil and the whole group behaves more or less as a block containing the piles in the soil. And so we treat that really as a large single block. And so we generally then take the lesser of the single pile capacities and the block capacity. And there is a simple transition equation which we've suggested that just smooths out that transition. But this is generally what we do in terms of assessing the capacity of the piles. And so again, these calculations depend on the single pile capacity methods that I mentioned before. Now, again, just a warning about the possibility of a weaker layer influencing the capacity of the pile. I did mention this before, and if we've got a single pile that's driven into a stiff layer with a weaker layer underneath, and maybe you will do a test pile and you find that, okay, that test pile is good, it's what we expected, and it's really not much affected by that weaker layer. But what you also have to recognize is that if you have a group of piles driven to the same elevation in that stronger layer, that now the weaker layer as a function of the overall diameter of that group is much closer, and it will have a greater effect on the group than it has on the single pile. So again, be very careful that when you do that calculation, you allow for that effect of the weaker layer underneath. I'm going to now come on to the settlement issue and talk about the settlement of single piles, and I'll restrict my comments to methods based on the elastic analysis of piles. And there are two basic approaches here. We can use closed form solutions. The most well-known of those is Randolph and Roth, who simplified the soil profile into either uniform profile, uniform stiffness with depth, or what they call the Gibson soil profile, where the stiffness increased linearly with depth. So they got some very neat equations, which I'll show you in a moment. The other approach is one that Professor Davis and I developed using chart solutions based on numerical analysis. So firstly, in Randolph and Roth's equations, here is the pile, here is the assumed distribution of soil modulus with depth, and you can have a stiffer layer on which the piles bear. And then you have an equation, and again, I won't go into detail on this, it's quite well documented in the literature, but this is a neat equation which relates the load to the settlement of the pile in terms of the characteristics of the soil and of the pile itself. Now, the second approach is using chart solutions that are based on numerical analysis. And so in this particular case, if we just look at the case of a pile in a uniform layer, we've got the load multiplied by a basic factor with correction factors for stiffness, layer depth, and modulus, Poisson's ratio divided by diameter divided by modulus of the soil. Perhaps one of the advantages of this approach is that these graphs that I'll show you give you a quick visual appreciation of the effect of various parameters. Now, of course, Randolph's equation you can put into a spreadsheet, and that you can do very quick calculations, but this gives you a visual appreciation of the effect of the parameters. So if we just go through these very quickly, this is the basic parameter showing the settlement factor as a function of length to diameter and also as a function of base enlargement. And what this tells us is that the longer the pile of a particular diameter, the less it settles, which we would expect. It also tells us that if we've got an enlarged base on the pile, it has a good effect when the pile's short, but it has very little effect when the pile is long. So that's useful to know. This is a correction factor for the pile compressibility, because if the pile itself is relatively compressible in relation to the soil, then a lot of the settlement of the pile will come not so much from the soil, but from the actual compression of the pile. And what you find is that if you've got relatively long piles, and this is the compression correction factor here as a function of the relative stiffness of the pile, going from very compressible piles to very stiff piles, and you've got curves for piles of increasing slenderness. As you get to very slender piles, then the settlement correction that you have to apply can be 2 or 3 times the settlement you would have if the pile was actually stiff. And then if your pile sits on a stiffer bearing stratum, then you can also apply correction factors to allow for the reduction in settlement because you're on a stiffer stratum. And these are graphs that tell you for different length to diameter ratios how much reduction you get in settlement, depending on how stiff your bearing stratum is. Now, this is a correction for soil piles in a soil layer of finite depth, and you find that unless the pile is very short and unless the layer is very shallow, you get relatively little effect of the soil layer depth on settlement. And finally, Poisson's ratio is generally not that important. Typically, we have Poisson's ratios of the order of 0.3, so you have a very small effect of Poisson's ratio. Now, of course, you should ask this question. All these solutions, and that includes Randolph and so on, all of these are based on the assumption of a nice uniform soil. But what happens if you've got a real situation where you've got layers of different characteristics? Well, it turns out that you can, with reasonable confidence, just take on the shaft an average, a weighted average of the modulus values along the shaft, and at the base you take a modulus characteristic of the soil or the stratum on which the pile bears. And so you convert your complex problem into a simpler problem. And this, of course, is one of the the interesting aspects and one of the, I guess, the bits of technical art that we use, our ability to be able to transform something which is relatively complex into something which is relatively simple, but still a reasonable representation of reality. Now, just to summarize some of the main characteristics of single pile behavior, one of the important things that we should recognize is that because the major mode of load transfer of a pile is by shear, then the major part of the settlement is immediate settlement because shear settlement is an immediate settlement. There is relatively little consolidation settlement that occurs with single piles in clays of normal proportions. The effect of compressibility becomes very important for long, slender piles because a lot of the settlement then is dependent on the pile stiffness itself. The other thing with long piles is that the settlement then becomes relatively little influenced by the soil stiffness at the pile tip. And it turns out that if you've got a pile that may be very slender, for example, the length might be 100 diameters, it really doesn't matter whether the pile is sitting on soil or on rock, the settlement will be very little influenced. The capacity may be influenced, but the settlement generally is not. The other important thing is that for piles of normal proportion in clay, the load settlement behavior is reasonably linear at normal working loads, so we can use elastic theory generally with an appropriate secant modulus. There are situations where nonlinear effects may be more important. If you've got piles in sand or piles with an enlarged base or large diameter bored piles, then there are methods that you can adapt to take that nonlinearity into account. But again, I don't have time to go into detail on those. Of course, soil parameters are very important. And how do we get those parameters? Again, we tend to rely to a large extent on empirical correlations with either laboratory data or with the usual sort of field data, the in situ test data, SPT, CPD, pressure meter. And most of these correlations we use are for a secant modulus at a typical design load level. And I should say also that, of course, one of the other methods of estimating soil parameters, which we may not have available to us at the start of design, is to actually do a pile load test and do an interpretation from that. But that generally is only something that we do in the later stages of design. And here are, for example, some very rough initial correlations for sands, a modulus of about 5 times cone resistance, over consolidated sands more, and in clays maybe 15 to 20 times cone resistance. So these are just first estimates that start you on your way. I mentioned yesterday in relation to the modulus values for shallow foundations that we are increasingly able to make use of the shear wave velocity that we measure from seismic cones or crosshole or downhole measurements in geophysical investigations of our site. And so we can get a small strain Young's modulus that's directly related to the shear wave velocity. And again, if we use a degradation factor that comes from the Fahey and Carter degradation function, we get this relationship showing that the modulus as a function of two things, the initial small strain modulus and the load level, the load divided by the ultimate load with parameters F and G here. And so, and this again is what Main has done. He said, okay, I'm using elastic theory, but I'm using a modulus which is itself a function of the applied load level, the applied load divided by the ultimate axial capacity. Now, what Main has showed is that for a whole series of case histories, and this is just one that he's used based on cone penetration data to get the ultimate capacity and shear wave velocity measurements to get the initial modulus. Here is load, here is settlement, and his predictions are the full lines and the dots are the measurements. And so there's quite remarkable agreement between the measured and predicted overall load settlement curves. But what I can suggest to you is that even if you're just using elastic theory at normal working loads, if you use the secant modulus, typically about 20% of the small strain modulus, that will get you to the ballpark figure of a relevant value of modulus for your pile settlement calculations. Now, that's single piles. Now we go on to pile groups. And I'm just going to focus for the time being on methods that we can do without the aid of computers. And I've mentioned three here: the settlement ratio method, the equivalent raft method, and the equivalent pier method. Now, the first thing we have to understand is that with a single pile, we put a load on and we'll get a settlement. And that is all there is to it. But where we've got a group of piles and they're all sustaining the same load, there will be an interaction because there'll be stress transmission between the piles through the soil. And so each of these piles will have an influence on each of the other piles. So we'll get an interaction between those piles. We can do analyses to tell us what proportion of settlement of a single pile we get if there's another similar pile at some spacing away from that pile. And by doing a superposition analysis of those interaction factors, we can finish up relating the group settlement to the settlement of a single pile. And again, I won't go through the detail of that. It's been fairly well documented, and it's rather disturbing that the first paper I wrote on this is now 53 years ago. So that tells you how long this has been around. But what we can do with that sort of analysis is we can actually distill it into a very simple practical approach. We can say that the settlement of the pile group is what we call a settlement ratio times the average load per pile multiplied by the settlement of a single pile at the average working load of the pile. So basically, it's a multiplying factor, RS, multiplied by the single pile settlement. So it's very simple. Now, that RS value we can get from theoretically derived values that have been tabulated in a paper in the ASC some years ago. But Randolph also recognized that there was a rather neat approximation that you could make where the settlement ratio is the number of piles to an index W. And as the first approximation, that W for floating groups in clay can be of the order of 0.5, and for groups in sand of the order of 0.3. So what that means, I mean, this is, again, a very nice sort of seat of the pants calculation, that if you've got a group that's a friction pile group in clay, then the settlement ratio is roughly the square root of the number of piles if it's in clay, and the cube root of the number of piles if it's in sand. Now, there was a more definitive settlement ratio that Randolph and Clancy developed, which relates also to the number of piles, the spacing between the piles, and the pile length. And here's the expression. The N is the number of piles, S is the spacing, and L is the length of the piles. So that gives you another estimate of the settlement ratio. So this is how we can very quickly estimate, as a first shot, the group settlement. Now, there's also another approach which was I think first suggested by Professor Beerham way back in 1957, the so-called equivalent raft approach. The one I'm showing you here is the one in Tomlinson's book. And what you do here is that you say, okay, I'm going to assume that this pile group is in effect equivalent to a raft that is embedded at some depth below the ground surface, and there may be some spread of load. So if you've got a uniform clay layer, then we can take that raft at about 2/3 of the pile length and the load spread at about 1:4. If we've got soft clay overlying sand, then we sort of spread the load down into the sand. And if we're on rock, then our equivalent raft is at the top of the rock. So what you can do once you've done that is you convert your pile group into an embedded shallow foundation, and then you can use elastic theory or conventional settlement analysis, one-dimensional if you like, which is reasonable enough to get the settlement, the average settlement of your pile group. So that's the equivalent raft method. The equivalent pier method simply transforms your pile group into an equivalent cylindrical pier. There's rough guidance as to what the diameter of the pier is, but you basically just replace the group by a single pier of equivalent, of the same length and of equivalent diameter, and then you use a single pile or a single pier analysis to get the stiffness of the pier and get the settlement of that equivalent group. So there are three very quick ways of doing this. Now, of course, there are various forms of software which enable us to be a little more refined in our analyses. And I've listed some of these that are available without going into great detail. There's Randolph's program Piglet, which you can still, I think, get, which is based on his work. There's a program called P Group that was developed by Professor Banerjee, which has now really been incorporated into a commercially available program called Repute. There's DefPig, which I developed many years ago, which I guess is no longer really available, but it's through the University of Sydney. There's a program called Group 7, which has been developed in the United States. And there's also now, in relatively recent years, a program called LPLA, which looks at pile groups and pile rafts, which has been developed in Canada. Now, I guess the question you should ask is, well, since we can do that sort of analysis, how will do the simple methods line up with what we can get with the more refined method? So we've done a comparison for both floating and end-bearing groups, looking at a relatively simple set of pile groups and calculating the settlement with the various methods. And this is for one of those cases. On the vertical axis, we have a dimensionless settlement. On the horizontal axis, we have the square root of the number of piles. So we go from a single pile to a 5 by 5 or 25 pile group for different values of the modulus of the lower layer, E2, to the upper layer, E1. And without going too much into, of course, here you've got a softer layer, here is a homogeneous layer, here is a situation where you've got a stiffer layer below the piles. The three colors, the green represents the computer analysis with DefPig, the red represents the equivalent pier, and the orange represents the equivalent raft. And you can see that once we go beyond a single pile, in this particular case, the computer analysis and the two simplified analyses give you pretty reasonable agreement. And I think that is really quite comforting, because what it indicates is that when we want to do a fairly simple check on our computer analysis, these equivalent pier and equivalent raft analyses seem to work fairly well. Let's move on now to laterally loaded piles. because this is the next issue we have to deal with after capacity under vertical load and settlement under vertical load. And here we need to address ultimate lateral capacity of piles, the lateral deflection of piles, and again with each of those group effects. Now, looking firstly at ultimate capacity, we have to recognize now that as with so many engineering systems, there are various modes of failure that are possible. And the late Professor Broms, in his papers in 1960, clarified that there are two main modes of failure. The first of these he called short pile mode, where the pile fails because the strength of the supporting soil is actually fully mobilized. So you've got failure of the soil supporting the laterally loaded piles. The second mode is what he called the long pile mode. And that's a mode where you've got perhaps relatively long piles, and the failure occurs not because the soil capacity is reached everywhere, but because the pile itself fails structurally. So generally you need to consider both modes and establish which is the more critical. We must also recognize that the conditions at the pile head can be very influential on the pile capacity. If we've got no restraint at the pile head, we have the so-called free or unrestrained pile head. If, however, the pile is fixed into a thick cap or raft, then it's a fixed head situation. There's no rotation possible at the pile head, and so you will get generally a much greater capacity laterally than if the pile head is free to rotate. Broms's theory, I mentioned, is probably still the most widely used method. It turns out that it's reasonably conservative, but it relies on statics and considers all of those modes. It considers cohesive soils with short and long pile failure with both unrestrained and restrained head, and then cohesionless soils with, again, those two head conditions and the short and long pile failure. And I don't have time to go into detail on this, but let's very quickly just look at the charts that Broms has developed for piles in clay. The upper curve shows a dimensionless ultimate lateral capacity as a function of the length of embedment of the pile. This dashed line shows the case for a fixed head pile, and these full lines show cases for increasing eccentricity of load above the surface of the pile. And what this tells you are two things. One is that the longer you make the pile, the greater the capacity of the pile, if there is no problem with the strength of the pile itself. And the second thing is you'll see that for the fixed head case, you get a substantial increase in the lateral capacity as compared with the free head pile, simply because if the pile is pushing all of it forward, you've got no rotation that's tending to hinder the capacity. So for short pile failure, that's the curve you use. For long pile failure, on the vertical axis, we have again the dimensionless ultimate capacity. Here now, we have a dimensionless moment capacity of the pile. And here we, of course, need to put into this theory not only the length and diameter and eccentricity of loading, but also the yield moment of the pile. And so again, what we find is that unless we have quite strong pile capacity, that once the pile is greater in length than about 4 or 5 diameters, it's generally the long pile mode that governs. In terms of pile groups, we do more or less the same thing as we did with axial capacity. We look at the mechanism of individual pile capacities, and so we calculate those and sum them all up. And then we look at the capacity of a block containing the piles in the soil and find out which of these is more critical. And again, we need to consider both modes, short pile and long pile modes, with the single pile capacity. Coming on now to load deflection prediction. Once we've got ultimate capacity, we need to get some estimate of the lateral deflection. There are three broad approaches. One of these, and probably the longest serving approach, is the subgrade reaction approach, where we model the soil as a series of independent springs that can be non-linear. And so we go through an analysis where we've got a vertical beam supported by springs, and we can do a computer analysis of that using the so-called PY method. We can also use elastic theory using the basic equations of Mindlin to come up with a relationship between the lateral deflection and the elastic properties of the soil and the pile. And then, of course, in more recent years, we can make use of finite element analyses using various soil models, linear and non-linear. But what we have to recognize here is that generally laterally loaded piles are truly three-dimensional analysis situations. We can't just have axial symmetry. I'm just going to show you some of these elastic solutions because, again, these are useful because they're so easy to apply. You can relate for a free head pile, the head deflection to the load and the moment that you apply at the pile head, and to two factors, which I've called FUH and FUM, which represent the effect of horizontal load on deflection and a moment on deflection. And in addition, with a free head pile, you can and need to calculate the rotation of the pile head, again, in terms of two different factors that are related both to head force and head moment. And with a fixed head pile, you have no rotation, so you have a very simple relationship that the deflection of a fixed head pile is related to the load through a factor FUF. And there are various forms of solutions and charts. I've just here, and of course you can't read this, but I will make these slides available. And if you've got very acute eyesight or a good magnifying glass, you can read these. And these are, I think, from Banerjee and Davies. There are many appropriate solutions here, but these are particularly simple to use. If you don't like these, you can use some of the charts that Davis and I developed. But in all of these cases, it's a fairly simple process. Once you've identified the characteristics of your soil, the modulus and Poisson's ratio, which is generally not important, it's fairly simple to calculate the lateral deflection and rotation. Now, just some important issues that I highlight here. What we have to recognize is that when we apply a load to the top of the pile, it's a very highly concentrated load, and we get very high lateral pile soil stresses near the top of the pile head. And so there is a tendency for us to yield the soil near the top of the pile. And so that, of course, gives rise to nonlinear behavior. So nonlinear effects tend to be much more important for lateral loading than they are for vertical loading. And there is also what is generally called a critical length, which is, or an active length, which is the length which, if you go longer, you have really no influence on the lateral deflection or rotation of the pile. So that critical pile length, as I mentioned, can be just a few pile diameters below the top. So the pile laterally is dependent on the soil in that upper few diameters. What that, of course, means are a couple of things. One is that because the lateral response depends largely on the near surface soil properties, those properties can be, in some situations, influenced by the environment, conditions. There may be unsaturated soils. The soil may be subject to moisture fluctuations. And so particularly if you've got a situation where the ground conditions can vary, it may be difficult to get accurate predictions of lateral deflections. How do we interpret the soil parameters? Well, you can interpret load tests if you've got that luxury. We found that you can quite nicely use pressure meter data to get a secant modulus, or you can use, which are not very much used, but plate load tests loaded laterally in a trench to get horizontal modulus values, interpreting those as lateral tests. And you can again make use of empirical correlations. And what we've found is that because under lateral loading, you tend to have higher strains in the soil than you do with axial loading, we generally have modulus values which are less than the values which we could use for axial loading. So as a first approximation, you can use modulus values which may be perhaps 70% or so of values that you would use for axial loading. Now again, just looking at pile groups, again, we have to recognize that with a group of piles, there will be stress transmission through the soil between the piles. And so there will be then those interaction effects, which means that the displacements will tend to increase due to interaction. And you must also look at the possibility that lateral loading can influence vertical equilibrium as well. And the mode of bending can be influenced by the shape of the group. It is possible to do theoretical calculations to look at these interaction factors, but it tends to be rather complicated because instead of just one interaction factor that we have, as we have in settlement, because vertical load on one pile produces only a vertical settlement, generally at another pile. Here, when you have a lateral load, you produce both lateral deflection and rotation at another pile. And it also depends on the orientation of the two piles as to what those interaction factors are. In general, you can still make use of group deflection ratios in a similar way to what we do for vertically loaded groups. And Professor Randolph and I checked out our programs, Deaf Pig and Piglet, some years ago by applying them to circular pile groups of 5 and 10 piles. And this is just the deflection ratio versus the load per pile, so that's the load level. For the 5 pile group, the measured values showed that there was a group factor of about 2. In other words, the lateral deflection was roughly twice the deflection of a single pile subjected to the same load. And Randolph and I got values that sort of bounded those. And for a 10 pile group, we got increases in lateral deflection somewhere between 3 to 5 times that. So, I mean, roughly this was, again, the square root of the number of piles in this, in both of these sort of cases. So there is definitely a group effect, and it's possible, again, particularly with the use of modern software to get a better indication of what those group interactions are. We did also do an exercise, and this was done with the gentleman developing Repute, where he was interested in comparing his program with other programs, Deaf Pig, Piglet, and another program called GPAM, which one of my former PhD students, Dr. Kenneth Zhu, developed. And so it was applied to this fairly straightforward problem: vertical load, horizontal load, and moment. And we looked at what values we got from these programs. So we looked at central settlement, lateral deflection, axial load in the front pile, lateral load in the front pile, and bending moment in the front pile. And these are Def Pig, Piglet, GPAN, and Repute in that order. And all of them give reasonably similar results. And I guess that's also fairly comforting, because what it means again is that what tends to be most important is not whether you use one program or another, but what the input parameters are for the program that you use. I want to now just finish off this sort of theoretical part just by alerting you to what may be an important issue in some cases, and that's the possibility that you will get external sources of ground movement that influence your piles. Here is the situation. There's 8 situations here very quickly where the soil consolidates and you've got piles in the ground. That can lead to a down drag or negative friction. If the soil is actually expanding, that causes an expansion of the soil and so uplifts the pile. A common situation increasingly in urban areas is where we have tunneling operations. The tunneling itself causes lateral ground movements, and these can affect our piles if you've got an existing building with piles. If you install piles adjacent to existing piles, the ground moves, so that affects the piles. If you've got unstable slopes, that can interact with the piles. If you have piles supporting embankments, or you increase the embankment loading, that can affect the piles. Excavation causes ground movements which affect the piles. And even building a new building, you increase the stresses, so you cause ground movements, and that will influence the piles. So when we look at analyses, the most effective way, or I believe, is a 2-stage process where you estimate what those ground movements are due to whatever are likely to cause them, and then do a foundation soil interaction analysis to see what happens to your existing piles. Because generally the major issues are what forces, what shears, what bending moments, and what additional settlements and lateral deflections are caused in our piles by these ground movements. The most apparent situation with ground movements is negative friction. I think most people now involved in foundation design recognize the phenomenon of negative friction, which is what happens that you get a downward shear stress generated because the soil is settling past the pile, and it gives rise to what is often called the down drag force in the pile. And that can be very large. And I mean, forces as large as 9 meganewtons have been recorded in piles that bear on rock, on clay, where the clay is settling. And so people have been concerned that that actually can cause failure of the piles, that you get that additional axial load, and that will cause failure of the pile. Well, it doesn't actually cause geotechnical failure of the pile, because to get failure of the pile, all of the pile has to move past the soil. What it does do, however, is 2 things. It causes additional settlement of the pile, and that may actually cause the pile to become unserviceable, so that the settlement is so large that it looks as though the pile has failed, but it actually has reserve capacity. The other possibility is that the axial load in the pile generated by the negative friction will actually cause a structural failure of the pile material itself. So these are the 2 major issues. So negative friction doesn't of itself cause classical failure, but it can cause settlements that are really large, and it can actually cause structural failure of the pile. With piles in swelling or expansive soils, we need to ask the questions: how much will the pile move upwards? What forces, tensile forces, are induced in the pile? The analysis, in fact, is very similar to negative friction, except that now we have the tendency for the pile to move upwards, so we tend to have no base resistance, and problems arise because expansive soils tend to be unsaturated and the soil properties tend to vary with moisture content and soil suction. This is a very simple diagram which has been obtained from elastic theory, but gives us again the first estimate of, answering the first question, how much movement do we get if the pile is in an expansive soil? So on the vertical axis, we have the ratio of the pile head movement to the soil surface movement. And we're assuming that the ground movement varies linearly from S0 at the surface to 0 at a depth ZS. And on the horizontal axis, we have the depth of soil movement going ZS on L from 0 to twice the length of the pile. Now, if, for example, we have a pile where the soil movement only extends down to, let's say, halfway along the pile, so ZS on L is about 0.5, then what we find is that the pile head movement, because of the interaction effects, is only about 0.2 of the soil surface movement. So the nice thing about this simple little diagram is that you can work out what sort of embedment you require of the pile so that you reduce the pile movement to an acceptable value. Very briefly, I just mentioned, again, these sort of situations where now you've got lateral movements exerting effects on the piles near retaining structures, unstable slopes, embankments, excavations, tunnels, and near newly installed piles. And in all of those cases, the key issues are this, that you get additional horizontal movements of the piles and additional bending moments and shears. And so for structural serviceability and integrity, you need to be able to estimate what those movements, bending moments, and shears are. How do you do that? Well, of course, you can undertake a fairly complex computer analyses these days with programs such as Plaxis and so on. We have developed a series of charts. This is one of a number of charts which we've developed, just trying to answer questions in terms of the maximum moments that you develop in a pile. I won't, again, try and describe these in detail, but these three are for different length to diameter ratios. The curves are for different relative stiffnesses of piles, and this represents the relative depth of horizontal movement as a function of length of pile. And this tells you what proportion of that ground movement the pile experiences. So there are graphs of this nature that give you, again, a first estimate of what the effects of those lateral movements may be. Now, I'm just going to finish off by very briefly going through an application of some of these techniques, obviously a little more refined, looking at the Burj Khalifa. And these are diagrams, these were the artists rendering, showing you what they thought it would look like. Now, the challenges here, the world's tallest building, we had carbonate soils and rocks where the capacity was less than it might be in normal ground conditions. There were concerns about cyclic loading due to wind and seismic issues, and there were differential settlement problems. This is what the site looked like at the time of site investigation in 2003. And just behind here, I'll point out that we did the design for these two towers, the Emeritus Twin Towers, which at the time were the 9th and 17th tallest buildings in the world, 355 and 305 meters. There was a lot of ground investigation done, 30 boreholes, SPTs, pressure meters, piezometers, and geophysics. This is the ground profile. Without going too much into it, there were basically a series of layers of cemented calcareous soils, which were basically soft rocks, calcareous rocks, typically with unconfined compressive strengths somewhere between about 0.5 to about 3 megapascals. The initial design for the tower was 196 piles, 1.5 meter diameter, and about 47.5 meters long. Around the tower, there was a podium, very extensive podium, with 750 piles, 0.9 meter diameter, 30 meter long, and the raft itself was 3.7 meters thick. So, I mean, quite a thick raft. And I'll say a little bit more about that in a minute. This diagram is a bit of a messy diagram, but what it shows on the left of the tower are other tall buildings, just comparing it. But what I included this diagram for was just to indicate to you on scale what the piles look like, as a proportion of the height of the building. Now the piles are roughly 1/16 to 1/17 the length or the height of the building. So really, they're relatively shallow embedment as compared with the height of the tower. So it's good to get some perspective on what is supporting this huge building. This is the tower layout in 3 wings. We acted as geotechnical peer reviewers for HIDA on this. We did independent settlement calculations, different methods, and we got quite similar results indicating final settlements of the order of 65 to 75 millimeters. There was a load test program done. I won't go through this in detail, but quite a few load tests done on full-scale piles. And what those tests did was they indicated that, in fact, the behavior of the piles was better than we anticipated. The skin friction values were larger, the axial stiffness was greater, cyclic loading had little effect, and the lateral stiffness was greater than we predicted. This is then a plan of the measured settlements at about 80% finality of the structure. And we find here a very nice symmetrical settlement where the maximum settlement's near the center, and there is a differential settlement of up to about 14 or 15 millimeters. Even though the raft is very thick, there is still a differential settlement between the center and the edges. These were our predictions of the final settlement along one of those wings. We predicted 75 to 80 millimeters. At the final time that we had records for, there was about 43 millimeters, and it was estimated that the final settlement would be in the order of 50 to 55 millimeters. So that was actually quite satisfactory. We were conservative, but not that bad. Just to put it in perspective, the building itself is predicted to shorten about 300 millimeters due to actual self-compression of the building itself and to shrinkage of the concrete. So our settlement of 50 or so millimeters is much less than the actual shortening of the building. And that, of course, was a big thing that the Burj Khalifa opened on the 4th of January. And you can see here, and those of you that have been to Dubai, that it does show quite a prominent, it is a very prominent feature of the Dubai skyline. And just finally, just to indicate to you that we can go even taller, that this is the Dubai Creek Tower, which is currently under construction. It will be, I think, certainly in excess of 1,300 meters tall. It is founded on 144, the central part, on 144 barrettes that go down about 70 meters. So it's a huge foundation. This on the right is where they're at the moment. I think there's been delays in the construction, but it is onward and upward for the people in Dubai. And so, of course, that presents us with future challenges for even taller buildings. So that is the end of my presentation. Thank you again. Right, look, I think if you've got tapered piles, the taper itself is beneficial in terms of increasing the lateral pressure. I'm presuming these are installed by driving, or you can put in tapered piles by casting different sections. But there are corrections. I mean, if I was doing it, I would use the work that Professor Nordland did way back in 1963, and I think there's a little bit of that in my earlier book with Davis on the increase in skin friction due to that tapering effect. So there is definitely a benefit in terms of the compressive capacity, and you would apply a magnification factor to the capacity. There is, however, one caution that I would just mention here, and that is that if you have tapered piles subjected to uplift, then you have to expect that the benefits will be perhaps less than in compression. And in fact, there may be negative benefits because the pile may be tending to move upwards into a cavity. So just be very careful with tapered piles under uplift loadings. I have indeed emphasized the importance of selecting parameters. And I think if I'm involved in a project, I try and do it in a number of ways. Firstly, I look at simple correlations with SPT and cone penetration or pressure meter or dilatometer. All of these methods of in situ testing provide us with a first estimate basis for our parameters. And in many ways, we rely on those parameters for our initial design. Now, going beyond that, again, I've indicated to you that I believe that there's a great potential for using geophysical methods to get at least estimates of the ground stiffness for settlement and lateral deflection predictions, simply because the shear wave velocity is something that we can now very readily measure. And what it does identify is within the mass of soil that is participating in the foundation support, it identifies any defects or any shear planes or whatever, and that's reflected in the shear wave velocity. So I think by taking the shear wave and calculating it, the small strain modulus and then decreasing that modulus, you can then get a better handle on the modulus values. Next, and this is something that we generally would do towards the final stages of construction, in a major project, we would try and ensure that you have some form of load testing of the piles themselves. And the value of those tests is, firstly, that you can construct the piles to the levels that are required. Secondly, that the performance of the piles is as you predict. And if they're not, then you can modify your design. In general, what we've found is that the performance of the piles in the load test tends to be better than we predicted because we tend to be conservative in our designs. And so, and this was in fact the case with one of the towers I worked on, the Incheon Tower, we were in the process of going back to modify and economize the design on the basis of the very favorable load test results. That project, unfortunately, was stopped for financial reasons. But I have been involved in projects where the test pile performance was inferior to that which we had expected. And so there you can modify the design accordingly. Now, the fact that you've got pile load test data, particularly if it is data that is on instrumented piles and perhaps in modern days done with Osterberg cell testing, is that you can then get quite detailed distributions of skin friction and end bearing, and also of the stiffness of the ground from your pile test information. And so, we start off with empirical correlations, we go to interpretation of in situ wave measurements, and then to actual interpretation of load test data. So there's an evolving process here of getting the parameters. Oh, yes. Look, I haven't touched on the issue of earthquakes. It is increasingly an important issue in design, and there's nowhere on the planet that's immune to earthquakes. And in fact, in Melbourne, a few days ago, we had a 5.9 earthquake, and that's sort of extraordinary. There are approaches. What we normally do is that we try and carry out a site response analysis so that we impose time records for a suite of earthquakes considered to be relevant to our geographical location. And we find out how those earthquake excitations are transmitted onto the foundation. And then we can translate that to movements of the structure itself. In general, what we do with that information is also that we provide earthquake spectra to the structural designers so that they can incorporate that into their own designs. But you can indeed, from that sort of analysis, work out what sort of ground movements and foundation movements that you might expect during the process of the earthquake. Now, one of my other former PhD students, Dr. Ali Tabesh, and I wrote a paper, I think in the Institution of Civil Engineers some years ago, might have been 2007, just doing some rough design charts on that sort of issue of induced moments and deflections during earthquakes. Perhaps you can refer to that. Oh, very good question. Look, there are methods that have been developed. My friends and colleagues in Melbourne, particularly Dr. Chris Haberfield and Dr. Julian Seidel, Ian Johnston, and my former colleague Philip Pells, they've done a lot of work on design of rock-socketed piles. And Carter and Kulhawi, if you refer to some of their work back in the 1990s, they have approaches for estimating the lateral deflection and stiffness of socketed piles. All I can do is I can refer you to those solutions, and there are also some nice solutions from elasticity that were published by Deeks and somebody else. I'm sorry, there were two authors in Geotechnique in 2003. Now they're all to do with deflections. In terms of ultimate capacity, you've got to be very careful that, again, you look at not only the possibility that the socketed pile acts as a laterally loaded pier in a cohesive material, but you also need to have a possible look at the development of a wedge failure. And so, again, like any good engineer, you would look at that possibility of having a wedge failure as well as having a failure due to basically lateral push. But by and large, really, you just use a different set of basic solutions for deflection that are focused on a fairly short pier rather than on a single pile. Look, I believe you can, but you've got to be very careful. When I talk about ultimate capacity, I try to emphasize this during my talk. We generally calculate an ultimate capacity as one of the limit states that we have to satisfy, that the ultimate capacity has to be big enough. But what we also have to calculate is the serviceability. And I believe that the ultimate capacity, if you're not concerned about how much deflection it takes to cause full failure of shaft and base, that you can certainly add the two together. I mean, in reality, part of the problem with CAPWAP is that you may, in fact, not be able to put enough energy into the pile to actually fully generate the end-bearing capacity. And so I think if you add your assessed skin friction and end bearing from a CAPWAP, you will tend to get a value which could be in fact conservative if you're really trying to calculate the absolute ultimate capacity of the pile. But yes, I mean, normally I would be reasonably comfortable to add those two components together. Right. Look, I can answer, or I will answer that question in this way. Anytime that you have a situation where the ground is going to move past the pile, then you need to look at the possibility of negative skin friction. Now, if you've got a very long pile, it may well be that the settlement may not be big enough to generate the full skin friction along the entire length of the pile. For design purposes, we usually make the conservative assumption that we can, but it may not be realistic. Okay, so that's the first part of the question. The second part is, if you've got a soft layer sandwiched between two stiff layers, the soft layer, particularly this may happen if you've got a reclamation, that you've got fill, which may be reasonably stiff, on soft clay, and then you've got a stiffer stratum. Yes, the problem here is that the soft clay will tend to settle, and of course, the stiffer layer above will also settle. And the problem with that is that you get or have the potential of fairly large friction in that stiffer upper material. Even if the friction in the soft clay is not that great, the friction in the upper layer may be quite large. So that's a fairly dangerous sort of situation that you have to be aware of. And it's particularly important, shall we say, for situations like a pile supporting embankments or bridge piles that you have to be aware of that. Okay. Excellent question. I'm a strong believer in after you've driven the pile, waiting a suitable period of time before you restrike the pile and use the results for an assessment of capacity and pile performance. How long is that? Good question. I would say with piles, I mean, there are calculations we can do to give us an indication of how long it would take for full dissipation. But generally, I would say in clays, probably 5 to 7 days, absolute maximum. In sands, there are issues with sands because particularly in some situations, you can actually have a relaxation in sand. So it's generally a good idea to wait a few days if you can. And so if you can arrange your pile driving sequence so that you leave a few days between the initial driving and when you come back to redrive, I think that will give you a better indication of how the piles will perform in service. Okay, good question. We did that basically, the designer took that into account in a fairly complex three-dimensional finite element analysis. What they did, HIDA did then, was that they modeled the foundation in 3 dimensions. They put on the vertical load, and then they put on the lateral load in the moment. And this is generally, again, what we do when we're checking buildings, that we model the entire foundation subject to all the loads. We factor down the ultimate capacities of the piles laterally and vertically, and we factor up the loads and make sure that the factored down capacities with the combined loading are adequate to resist the factored up loads. And we find that to be a very satisfactory approach to take. It does mean that, of course, you have to have that sort of 3-dimensional software, but I guess as time goes on, we are becoming more and more used to doing that sort of complex analysis, particularly when we've got projects such as the Burj Khalifa, where we've got $1.5 billion worth, and in the I think in the Dubai Creek Tower, the cost of that will be something like $4 to $5 billion. So you can afford to do good ground investigation and top-notch analysis. Thank you very much again for inviting me, and thank you for facilitating this. And thank you to all of those people who were brave enough to listen in to these 2 talks.